Okay, good morning or good afternoon, depending on what time you were watching this video clip. Um, I want to talk about now dot product and all the inner products. Okay, of the two factor, either in two-dimensional or three-dimensional. Okay, we have the same process for them. Okay, the dot product or inner products, or sometimes we also call scalar product, but I think I always call it dot product. Okay, dot product here. The resulting of this product is going to be the scalar, or it's just a number. Here's the important thing. Alright, so when you it's like a multiplication between factor, but multiplication I already mentioned in the previous EP, right? The multiplication of factors doesn't appear here as the like a number in when we study real number system, but here we have dot product, just like a multiplication for between two factor, but when you multiply them, the result of this kind of multiplication, you will get scalar, not the factor back. But there will be another case that you can consider is as a multiplication between factor. Is going to be cross product, but that thing applying for three-dimensional factor only. Okay, anyway, just consider the dot product in this video clip. So we have this definition, you have vector A and vector B, and then you want to find the dot product vector A dot vector B. It's going to be this definition, modulus of A multiplied the modulus of B time cosine theta, where theta have to be between 0 and pi. I think this is not quite right. I think I have to, well, yeah, it does. That's okay. Theta and pi, and the angle have to be between A and B. Okay, it's the angle between vector A and vector B, but I have to explain how we measured this theta. Okay. Well, in general, when you have vector, right, two vector, you can have, when you visualize it, you might have this and this. This is vector A, this is vector B. Well, this one is obvious that theta is here. Okay, but in another case, when you draw it, you might get this vector, say this is vector A, and then you have this vector B, for example, and then you will say, oh, here should be theta. The answer is wrong. Okay, when you want to measure theta, it has to be from tail to tail, so you need to translate vector B down here. This is the new vector B, and then the way you measure theta have to be from this and this. Okay, not that vector, not the original one that I draw it. That's what's wrong. It has to be like this, so you have to move vector B down to the tail of the vector A. Okay, so you will have three cases, okay, for the situation that you have two vector, the angle between two vector, three different cases. The case one, when you have theta is the x cube, and then you have theta is pi over 2 or 90 degree or right angle, and or another case is when theta is obtuse. Okay, and how do we compute theta? Well, to use the definition of dot product. Okay, so let me derive it for you. You have A dot B is equal to length of A times length of B, right? Cosine theta. So then you move the modulus, two modulus to the bottom of this fraction. Okay, so if you want to find theta, you use the arc cosine, inverse of cosine. So then you get this formula. Okay. All right. So so that we have three cases here. We wanna classify the angle. This is the theorem for the classification. All right. If theta is x cubed, well, sorry, let me revise it. Theta is cubed if and only if a dot b is positive. When you have positive dot product positive, right, then cosine is going to be positive. And if cosine is positive, theta have to be in the first quadrant. So that is why theta is x cubed. Another case, theta is obtuse if a dot b is negative, right? If a dot b is negative, cosine theta is going to be in the second quadrant. Okay, so that's why. And I think the most important thing is right here. If a dot b is 0, then theta is pi over 2. Okay, because remember cosine 0 pi over 2 is 0, so that is the reason. Okay, cosine 90 degree is 0. So you get that, and we're gonna call this situation perpendicular. So A is perpendicular to B, right? And then we get to this definition, orthogonal vector. Okay, non-zero vector A and non-vector B are orthogonal to each other if and only if A and B are perpendicular. So this is another definition. If you want to write it, it's the geometric definition: A perpendicular to B, and then B perpendicular to A. All right. If you want it to be algebraic definition, you have to do dot product. A dot B is 0. Okay. So from this definition, the zero vector is orthogonal to every vector. The reason is because if you do A dot 0 or 0 dot B, both of them is going to be 0, right? Okay. In terms of dot product, you can also find the modulus, right? A dot A is going to be the modulus square. Okay, or in other words, modulus can be found by dot A and A to each other, and then you take the square root. Let me explain why we get this. Okay. From the definition, A dot A have to be modulus of A times modulus of B of A, and then cosine theta. But A and A, the angle between vector A and vector A is just 0, right? And cosine 0 is 1. This is just 1. So then you have A dot A is just modulus of A square. Okay, easy. Right, that is the relation between modulus and dot product. Okay. The definition, when you want to find dot product, you have to find the modulus of two vector and then multiplied by cosine of angle theta. But there is another way you can find dot product if you are given the vector with the coordinate form. Okay, with the coordinate I, j, k. You can find dot product by using this property. So given you have a vector A written as A1, A2, and A3 here. A1, A2, and A3. B is B1, B2, B3. This is for 3-dimensional, right? For 2-dimensional, everything works the same. You just ignore the last coordinate. Alright. Here's a way that you find the dot product, not just the original definition. You can also use this way to find dot product. A dot B, you just multiply the first component to each other, A1 times B1, and then you multiply the second coordinate to each other, A1 B1, and then A3 and B3, and then you add them all. Okay, if you add them all up, you're gonna get the scalar. Okay. Equation 5, which is the previous equation, show that dot product of two vectors is the sum of product of their corresponding component. Okay. For example here, if you are given three vectors, right, A, B, and C, written as you can see here, I don't have to pronounce it. Right. So we have A, B, and C. If you want to find A dot B, you just here, just show you only one example. You multiply. I think there's a mistake here. A, B, and C are the same. No, it shouldn't be the same. This example have a typo. B have to be, okay, let me cross this out. I think B is -3, 4, and 2. Okay, please change that in your document. For C, I think C is 3, 6, and 3. Okay, all right. So if you do A dot B, you have to multiply 1 to -3, and -2 to 4, and then 3 and 2, and then you add them up, you get -5. It's okay to be negative number. Okay, it's okay to have a negative number. If it's negative, remember theta is just obtuse. Alright, and B dot C work the same. A dot C is zeros. The conclusion here would be A is perpendicular to C. Okay, all A and C are orthogonal to each other. Okay, here's a conclusion that I just explained to you. Alright, now let's take a look at the example. Find the inner product of and the length of vector A and vector B, as well as the angle between these vectors. Alright, so first you find dot product A and B, you will get -1. The reason is because if you do it this way, 1 times 3 plus 2 times -2, and then 0 times 1, you have 3 minus 4, which is -1. That's a dot product. And if you find the modulus of A and B, you get square root of 5 and square root of 14 respectively. Alright, that's the dot product and the length of A and B. And then if you want to find the angle between A and B, then you will take the formula arcs cosine of A dot B divided by modulus of A times modulus of B, and that's the answer. Okay, this slide is going to be about the property of dot product, algebraic property. Okay, A dot B is equal to B dot A. Okay, just like addition, you can commute dot product. Okay, and you have a distributive here, A plus B dot C. You can distribute dot product C to the each one, A and B. Okay, A dot A is always either positive or 0. And this property we have seen it before. And scalar multiplication, K time vector A dot vector B can be done like this: K time A first, and then dot B, or A dot K time vector B. and we have Schwarz inequality. The absolute value of a dot b, remember a dot b is just a number, right? So then you don't have to put the modulus here, you just put the absolute value. It's less than modulus of a times modulus of b. That's an inequality. Okay, here's the important thing. Right, we have seen the modulus ij and k are the unit factor, right? So the modulus of these three factor is just 1. So you have this property, and also I think this is the most important for this property. I dot j, j dot k, and k dot I are 0 because each pair of these three factors are perpendicular to each other, right? I perpendicular to j, j perpendicular to k, and k perpendicular to I. Okay, that's the end of this slide and this EP. So thanks for watching again, and see you next video clip. Bye bye.